Good morning, everyone. Good morning. Welcome back. I trust everyone is doing okay. Hope you've enjoyed this the last few episodes on the Pythagorean triplets and the whole series so far. It's been interesting for me to continue along or channeling my passion for numeracy and mathematics here through C sharp, and I hope you're enjoying it too. So continuing on from the last two episodes, we've been looking at Pythagorean triplets and we've been expanding the idea, trying to streamline the process. We started at triplets, we've moved to quadruplets and quintuplets, and then we moved on to optimizing the script to cut out unnecessary steps and try and streamline the process. So that's been all well and good. And so we've built on Pythagoras's work and the work of other mathematicians who've attempted this problem. What we're going to do today, building on that, we've got the script from last week that we created, which is the optimized scripts for this is quintuplets so far. Yes, quintuplets raised to the power of 4. So I wanted to touch on something in similar vein. Um, this is Euler's sum of powers conjecture, the Euler's sum of powers conjecture. So um, it states that the sum of n many parameters raised to the kth power of positive integers is also a kth power, meaning that n, the number of parameters on the left-hand side, is greater than or equal to k, the power that the parameters are raised to. So this is interesting because it's not quite the original Pythagorean triplets, quadruplets, quintuplets exercise, but we're simply raising the power of those parameters. So I will show you what that looks like. I've pulled up this note on the right here to visualize what we're looking at. So we've got the original Pythagorean problem, triplets, the classic a squared plus b squared is equal to c squared. And then building that up, we tried to solve for quadruplets, quintuplets, etc. So Euler's sum of powers, the sum of n many powers on the left-hand side for the parameters. Here we've got, for the idea of triplets, we've got two parameters on the left-hand side raised to the power of 3. We've got, for quadruplets, we've got three parameters raised to the power of 4, etc. So Euler conjectured in the year 1768 plus 1, I think, that this didn't hold. There were no solutions for these expressions below. So Euler, it was merely conjecture. Euler did not really have the means or the processing power, dare I say, to prove this or even disprove this. But his conjecture stated that there were no solutions for these such expressions. Again, you can see the cognates with the original Pythagorean problem, but he's simply raising the power to 1 by 1. So that's why it's called conjecture. It could neither be proved or disproved. But Euler was making the case that there were simply no solutions to it. So we use this word conjecture, Latin, the Latin word meaning a collection of or together, and iacere, meaning to throw. So the classic con and iacere, to throw something together. So he was throwing together this idea without proof, but his evidence or his cases or his rigor proved that, or demonstrated at least, that there was no immediate solution. So what we're going to do is we're going to try and emulate this. So building on where we left off, we ended at the optimized quintuplets case. So with a few minor changes, we're going to change this to Euler's sum of powers conjectures quintuplets. So all we need to do for the first case is to raise this to the power of 5. So we're going to see if, or if not, there are any solutions. So let's do that. So this will be a simple case of changing the power. So if I simply search for all the powers, I won't explain this script in too much detail. I did that in the previous episode, which you can go and watch. So all I'm going to do for now is simply change that power. So give me a minute and I will do that. And I'm using the handy Control F function in order to do that. 1 second. Power 4, power 4, power 5 now. Oops, bring it back. And I don't need to change much else. The parameters are staying the same. So if I, do I have any more? Yep, no document count, so get rid of that. I'm going to try that again. Any fours? No. Okay, so let's see, do we have any solutions? So let's run this again for the final parameter e raised from 1 to 1,000. Do we have any solutions? Let's see. Uh-huh. We do have solutions. There we go. Okay, so there we go. Straight off the bat, we've got well, there we go. The conjecture has been disproven. So we can see here that there are solutions: 27, 84, 110, 133, 144. And you can see moving on, there are let's say multiples of the same solution. So 54 is 27 times 2. 168 is 84 times 2, 222, 110 times 2, etc. So this is a multiple of the same solution. And I believe the rest of them are also multiples of the same solution. So 54 plus 27, 81, 3 times 27, 108 times 4 times 27. I think, okay, I think. So that's what it is. It's simply multiples of the same one. So clearly the quintics to parameters come, let's say, few and far between. But there are solutions, meaning that Euler's conjecture has been disproven. So I'm not going to claim credit for this. This has already been disproven by the work of Landor, Parker, Selfridge. So Leon Landor, Thomas R. Parkin, and John Lewis Selfridge. So this has nothing to do with the department store John Lewis or the department store Selfridge. John Lewis Selfridge had nothing to do with those. I believe he was long before the opening of the first John Lewis or Selfridge department store. Who knows, maybe relative, but no evidence suggests that this was the man. So this was disproven in 1966, which means Euler's conjecture stood for 197 years. 197 years, Euler had his, let's say, his immediate thoughts as to why this couldn't be proven. He simply didn't have the processing power. So Leon Landor and Thomas R. Parkin, they were students at University of Michigan, I believe it was, and they had access to the IBM mainframes, so they could simply run this computation. John Lewis Selfridge was more, let's say, theoretical, in that he came up with the ideas, fundamental principles, parameters for outlining a solution. So it was Landor and Parkin that devised the solution. It was Selfridge that let's say, laid the groundwork for it to be proven and tested the rigor of their process. So that was 1966. They all came together. They managed to disprove it. So they used it, again, using a combination of the IBM mainframes and a programming language, Fortran. So to my fellow duelists who grew up watching Yu-Gi-Oh! No, I'm not going to make that joke today. No, I won't say that. Emphasis on the word today, but I won't make that joke today. So it's amazing how far they've gone. They didn't have access to R, no C Sharp, C++, Java, etc. They had Fortran, etc. to contend with. So there's another case where we can go back and look at the quadruplets case. But I'm not going to do that because, well, I'll come back to that later. But for now, here we go. We've got the solution for the quintuplets. So these are not Pythagorean quintuplets. They are simply quintuplets that's serve to, let's say, disprove Euler's sum of powers conjecture. So let's move on. Going back to the sheet we had, there we go. So we've gone through that. I'm going to simply strike that out so I remember our progress here. Strike that out. And we're not going to go back further, but the quintuplets case has been disproven, let's say. So let's try and build this up. And I want to move now to the Pythagorean heptuplets case. So a to the 5, b to the 5, etc. So I'm going to base it off this same script. So in fact, I'm going to make another instance of C# and do this there. Okay, I've created a new instance of C# and I've copied the previous script over here. So what we need to do, we need to solve for this expression here. So now we've got 5 parameters on the right, raised to the power of 5, and that is equal to some other parameter, f, also raised to the power of 5. So this is what we need to solve. We need to add in the parameter 5. But remember, we need to, let's make that bigger, we need to let's say expand on the dictionary. So remember the previous dictionary for the quintuplets was simply two of the parameters raised to the power of 5 pre-calculated. But now we want to make that c as well. So three of the parameters. So we have six parameters, but we want to halve the amount of work. So I'm hoping it'll be a simple case to simply build upon this. So let's get on with that. So I'm going to change that to Pythagorean heptuplets. And now what we're going to be pre-computing the fifth powers. So I don't need to change the index. 5 is fine. 5 there. That is also fine. I to the 5. Everything is fine there. And this dictionary is c to the power of 5 as well. And I need to make a list here that one needs to see. So everything that's A and B needs to go to A and C. So that list there, A, B, and C, will be int C. Okay. And everything needs to be moved to the order of F, right? Yep, F. So what am I doing here? So there we go. That's 4 max. I think that will be F. Yeah, okay. I need to do F. F is the final parameter. F is the final parameter. Max F. This is probably going to be a lot more work than I thought. Max F. There we go. So we've got this is the main loop now, so I need to do something with this loop. Parallel 4, 1, max A, internal 4, and max F, B equals F. So I need to add another loop for that. Yeah, so okay, so that's 4. I need to run this through now. So C equals to that upper B above, and C is going to be less than or equal to the max F. C++, and this here, this big integer is also going to be amended, but I need to move that in there. Okay, so let's try that again. So big integer needs to be, what do I need to do here? I need to add the C in there. So that's still 5. 5, 5, 5. Yeah, plus power of 5 to C. Yep. Add list. So that still falls in that same dictionary. Well, this is the dictionary. So C there, I need, last thing I need to add something. It's still giving me some issues, plenty of issues, yeah. C, so return the existing. That's all I'm doing. I'm making A and B, the pair A and B to a triplet of A, B, C in the dictionary. Okay, now what? 5, that's going to be max F there. I'm not quite sure how much of this is interesting, just watching me replace these F's and E's to F's, etc. So that's it. That will be the final. I need to move this up to D. So this is something I need to pay attention to. D will be less than F as long as D is running. So the next one would be E. So I need E equals to, wait, no, yeah, E is less than F. Okay, and E is less than E. Okay, so the big integer powered would be the D sum, DE sum. So that's simply a name, so I'm not entirely concerned about that. E as well there. And that would be, I need to change that. That would be my F6 sum, and that would be my ED sum. Try to get out the value. So all I need now, oh, I'm not done actually, so there's still a bit of work to do. For each, is that you? It's the for each C, yeah, for each C in the ABC list. Okay, now I need to change something now. I've got an AB list. AB list. Okay, yeah, so that ABC list there would think it's not giving me an ABC list. Yeah, I think that will also be the ABC list as well, but our ABC list needs to link somewhere. What do I call that? The ABC list. ABC list. Yeah, out for ABC list. Yeah, I think that's fine now. Good. So that'll be int values new ABCD. They're calling me for DD. So these ABCDE are the left-hand side parameters. We're not done. We're not done. Join out. Yeah. So I need to add it in there. Right. So that E will still be values of E equal values 4. Yep. 4. And F will equal simply F. Nope, not false, but F. Okay, good. Now what? Am I on the right lines here? So I need to search completed. Yeah, so it's still finding an ellipsis there. What are my 8 lines here? So something's not right. Strong arguments. Let's bring that down to 10 at least to see if this runs. Does it run? I've got 8 errors. So I want to see what they are. What are they? Yeah, what is it? The best overload add method. What did I do here? Or what did I not do here? What is my... Bear with me 1 second. Forgot that. 3 integers in there. So now what? What do I have? How does that affect anything? You know, I still have... The name F does not exist. Why now? The D is less than or equal to F. Well, it should exist because well, it shouldn't because that's supposed to be F and F as well. Yeah, and I think this is also supposed to be an F. I simply glossed over it all. So I've got 2 now. What's your problem here? So that should be F6. Does that solve anything? No, it doesn't. Why not? What about DE sum? What about you? The name DE sum. Oh yeah, ed sum. DE sum, right? But F6, why does F6 not exist? The name F6 does not exist. Was I supposed to put F6 somewhere? No! F5. Concentrate. Yeah, no issues found. Okay, let's try that again. Okay, good. It's run. Good. All right, so searching for quintuplets. Do we have any? We have none between 1 and 10, but if I raise this to 100, let's see what we get. Great. Okay, there we go. So that's the Pythagorean quintuplet case, 1943, 46, etc. So this can be proven, actually, or I can calculate this, but not in Excel. I'm going to need some computing power for this. So for that, what do I need to do? I'm going to simply take these, and I'm going to go over. What do I want to do? Okay, so I'm back in programmers. I'm going to do something slightly cheating, but you know we worked in C# down here, but there's also Python up here. So reason why I'm working and I'm going to try and compute this in Python is simply because Python apparently doesn't have any limitations on digit counts, for example. So you know before in C# we had to use the what do you call it? The big integer function or the big function or the bool, all these other functions. In Python, apparently that's not a problem. So we can simply run this in Python, no problem. We don't need to make any adjustments for big integers, etc. We can simply run a simple script like this, and let's see what falls out. So I'm gonna just write this out real quick. 67. And this was the solution that we found, or C# found. I'm not going to pretend to take any credit for this. Oh, goodness, come in. Print. Okay. That's first parameter. Let's simply output that as A. Okay, you're going to be B, C, D, and E. How does one do this? So this will be the actual. No, that's not how you do it. How do you blank line in Python? I think it's the hashtag. Yeah. So sum of all the fifth powers. Okay, so total that sum will be A plus B plus C plus D plus E. So what do I want? I want a console right line. No, I don't. I want print. Sorry. Print, and this will be the sum of all fifth powers equals. And what is that going to equal? It's going to be that total I said earlier. And what do I want to measure that against? I want to measure that against, what was it, the f of my solution, which was f to the 5. And I want to print that. So print something, give it a name. I can call whatever in there, f to the 5, f to the 5th index. Okay, so what does this look like? Great, so, yeah, okay, there you go. The 5th looks, yeah, this is the same. There you go. 1,934,917,632. They're the same. Okay, so that solution holds up, meaning we found a solution for the Pythagorean quintuplet. No, heptuplet. It's the heptuplet. Good. So I'm pleased with that. That is a 19 to the 5, 43 to the 5, 46 to the 5, 47 to the 5, 67 to the 5, and this is your 72 to the 5. That's the sum of all the parameters on the left-hand side. So that's all well and good. So let's continue on now. We've got 10 minutes there, so I want to continue on this vein. Yeah, okay, let's go back to it. So going back to Euler's sum of powers conjecture, let's prove if there was anything above that. So if we set k to the power of 6, so all I'm going to do now is simply change the 5 again, as what I did earlier, to 6. So let's change everything to from 5 to a 6. 6. Okay. 6. 6. Say. Any more? Plenty, obviously. F to the power of 6. 5 to the power of 6. No. 6. 6. There 6. Come back here. Okay, there should be no 5s in here. I don't want any 5. Oh, yeah, okay. So this was, let's make a note of that. This is the Pythagorean quintuplet, okay, which we did find solutions for. Solutions found. So I'm simply going to state that. Solutions found. Solutions found. So that's good. But what we're doing now is Euler's sum of powers conjecture. Okay. So this is still a quintuplet, but these aren't Pythagorean quintuplets. Let's see. They're simply raised to the power of 6. So it doesn't matter. Euler's sum of powers conjecture has been disproven, but let's see how far we can take this. So let's go. I want to try and speed things up a bit here. Okay, let's run that. And let's see if we get anything, which I doubt, because this is a very large sum. This is heptuplets now we're dealing with. And if you look at what's going on here, I've got a bit of a problem. I can feel my computer slowing down. Just look at that processing power. Just look at all of that processing power being occupied there. It's funny. Well, oh gosh, look at that. So what you see when I bought this laptop, this is a Dell, by the way. I bought it back in July or sometime. They ran me through a checklist process where they asked me what I wish to use the laptop for, and I can feel it. My laptop is slowing down. This is a lot of processing power it seems it's using. I disclosed the typical Excel sheets, YouTube, personal banking, etc. I don't believe there was an option for programming. It didn't mention C# or anything like that. What else? Do you wish to commit acts of heresy against the crown and the sovereign? Do you wish to destabilize and or topple South American governments or any such despotic regime? Obviously, I checked no to both. But nothing said anything about potentially wrecking your CPU with the use of high-intensity calculations in pursuit of Pythagorean triplets, or trying to disprove the Euler's sum of powers conjecture, which has already been disproved. Okay, so this really is slowing down a bit. I'm going to try and cross it out. It's not letting me cross it. Let's give that a minute. Oh, I simply had to close that down. It wasn't getting anywhere. It was slowing the computer down. But I think you guys get the point. We have. I'm going to go back to my other C# program, and I can see if let's see if I can maybe expand that and run that. So this is Pythagorean. No, this is not. This is the Euler's conjectures quintuplet. So maybe I'll just continue on that. There was for the quadruplet, so a to the 4 plus b to the 4 plus c to the 4 equals d to the 4. A gentleman by the name of Noam Elkies discovered a solution in 1987, but the solutions were so vast. The first solution, the parameter a was equal to 2,682,444. 440, sorry, was the smallest such solution he had. And you can see these are exorbitant numbers there. It was you can see why Lander Parker Selfridge, they found a solution for the quintic in 1966 involving small numbers, 27, 84, 110, etc. Noam Elkies found it a bit of a hard way in 1987. Not that Lander Parker Selfridge didn't bother trying beyond that. Not that they settled with shattering Euler's sum of powers conjecture to smithereens, but they did want to go further. They were simply limited by the IBM mainframes, Fortran, etc. So Noam Elkies presumably went along the same vein, but he discovered the method of elliptics, so elliptic curves, Diophantine equations to discover it. Um, and then later on, Roger Fryer in 1988 discovered let's say, a smaller solution to the quadruplet. So a to the 4, b to the 4, c to the 4 equals d to the 4. So a is equal to 95,800. And you can probably figure out why was it harder to solve for the quartics than the quintics. The quartics were, let's say, sparse. It's a lot harder to find a solution for quartics. They do exponentiate. However, there's less parameters to try and make the sum work. So for the quintic, it was much easier because there were smaller numbers to deal with, and you had that extra parameter to give it stability. In fact, there's a negative solution to it. There's negative 220, 527, no, 5,027, 6,002. I'm probably going to write that down instead of trying to eyeball that. So for the Pythagorean quintuplet, you had a negative solution. That being, if I've written it down here, so I don't have to keep regurgitating off the top of my head. 6 to 37, 140, 68, and 14132. Have I written that right? 14132. So that's a good point. We haven't specified here. C sharp is assuming we can only run with positive numbers, but really that is a solution. If you punch that into Python, you will get the solution. You will get all this raised to the power of 5. Hang on, no, this is Euler's. This is Euler's sum of powers conjecture. Okay, oops, don't do that. So yeah, if you run that in Python, you will get all that to the power of 5 will equal that to the power of 5. Um, so Roger Fryer and Noam Elkies, they you can argue did it the hard way. So you got to appreciate the work that's been done here. There's in 1957 there was Fortran, and then 1970 to 1972, I suppose we had C. 1972 was the initial release. MATLAB came out in 1984, the initial release. Maple, I believe, is more of a graphing tool. At least I used it when I was in university. I used it to make graphs. Maybe you could do more with that. I don't know. C++, 1985. And you can see they were severely limited by the technology of their time. C, MATLAB. There's no evidence. I was trying to do my reading on this, and there's nothing to suggest that Noam Elkies used Fortran or C, but I'm going to assume they could. I can't imagine how far they could have got without such a tool. So on a final word on this, let's see how far you can go here. If I raise that to 4,000 while I narrate. So I mentioned before this Euler sum of powers conjecture held for 197 years before being disproven. So other such conjectures we've got Merton's conjecture, formulated or proposed in 1919. It was disproved in 1958, 39 years. Fermat's last theorem, 1637, was formulated by Fermat. And Andrew Wiles came along with input from Richard Taylor in 1994. So for the expression x to the n plus y to the n equals z to the n, there are no integer solutions for n greater than 2 where x, y, and z are not equal to 0. So that stood for 357 years, so that would hold the record. However, Fermat's last theorem was proven by Andrew Wiles. Euler's sum of powers conjecture was disproven. So for the Euler's sum of powers conjecture holds the record for the longest time held until being disproven. What else do we have? We have other possible contenders. We have the Goldbach conjecture, which was formulated in 1742. Every even integer greater than 2 is the sum of 2 primes. That was formulated in 1742. It hasn't been proven or disproven, which means it's 283 or so years later. So if someone were to disprove it now, that would take the new record. Euler's conjecture that there are no odd prime numbers, formulated in about 1750s or so, sometime in the 1750s, which means it's got 266 years. And there's one other very famous conjecture, which I will not state. I'll not state today, but I think you all know what I'm talking about. but I'll save that for another video. I mean, if I can find a script to run for this particular topic, um, I'm gonna try. I want to try and make that work. But for now, I'm gonna let that be for now. But it's amazing what you can do with C sharp or other such programming languages. Look, I made the point before. I mean, C sharp can do all this. It's disproven. C sharp has gone so far to at least prove these numbers for me. Um, I made the point before. Is it possible to destabilize a South American government using C sharp? Probably not. Is it possible to even destabilize a South American government? Probably. Is it possible to disprove Euler's sum of powers conjecture using C sharp? No, it's already been disproven. So you don't need me for that. And if we're going to go further in all of these cases, maybe heptuplets, septuplets, etc., to disprove things, it's not going to happen by some guy on a Dell computer in the middle of the work week trying to produce these numbers. It's not going to happen. But someone else will do it, not me. And with that, I've rambled on quite a bit. I'm not quite sure how much any of that was useful to you, but I found that reading particularly enlightening moving forward. So I'm going to end this video here. I'm not done on this episode with the Pythagorean triplets extended and also the Euler's sum of powers conjecture. There's one more thing I want to do. I'll save that for next week's video. What is it? September 8th, 2025 today. It's Monday. I'm going to get this video out soon. I hope you enjoyed it. As always, any comments, any thoughts, not only on the programming, but the history, but the mathematics, figures, etc. I'm always happy to hear your thoughts and always happy to try and make things better for you. So anything you want to say, anything you want to write, please do so. I'm always happy to read your thoughts. So yeah, have a good day, everyone. Have a good week, and I will see you next week for the next episode on this series. Thank you very much. See you soon.